always a bit dangerous to mix physics and philosophy, but this video is for anyone interested in getting a foothold in the discussion about how quantum mechanics challenges a lot of people's notion about how reality works. I'm recording it in the wake of the announcement of the 2022 Nobel Prize in Physics for three experimentalists who won the award for something termed establishing the violation of Bell Inequalities, which in turn led to a spate of news headlines and articles featuring buzzwords about proving something related to quantum and reality, weirdness, and spooky behavior. In reading these articles, there's a bunch of jargony terms, such as the one shown here, that could be challenging to make sense of, ending with the aforementioned Bell inequality and the associated term Bell test or Bell experiment, which, to be clear, refer not to a musical concept, but to the late Irish physicist John Stuart Bell, who wasn't able to share in the Nobel Prize for the experiment he thought up because Nobel contest rules state you have to be alive to win. Multiple people I've run into have been generally interested in what this celebrated experiment is all about and have tried to read some of the aforementioned popular accounts, but usually found them unsatisfying. As best I can tell, the issue is that the popular accounts often contain assertions and analogies, but don't really explain the step-by-step reasoning of the assumptions behind the experiment, enough details of what's being measured, and how the results lead to surprising conclusions. One remedy for this confusion is to read a more technical explanation of what's going on, and there are some good streamlined accounts of Bell tests, a couple of classic versions of which are linked to in the description. However, I think for most people, the math that's used, even in these streamlined versions, is a barrier to understanding what's going on. Either people don't want to deal with math at all, or, working through the math, they can lose the thread of the larger reasoning about what these tests tell us about reality. So, to help all those people who find themselves caught between these two approaches, I've created this video, a non-technical but step-by-step explanation of a Bell experiment that uses just pictures to walk through the assumptions, experiment, results, and conclusions. Now, one disclaimer is that in order to eliminate the math part of the story, I've had to alter the actual predictions and results of quantum mechanics and simplify the details of the experiment. So, you shouldn't make too many inferences about these specifics from this video. What I've done my best to preserve faithfully is the chain of logical reasoning and observations that make this type of experiment philosophically interesting and worthy of a Nobel Prize. Our story begins with a rock, an otherwise ordinary-looking rock. One day, you're holding a sheet of paper near the rock and notice a small hole has spontaneously appeared in it. Where did this hole come from? You hold the paper in the same location for a while and notice more small holes appear, one every few seconds, clustered around the same spot. This is a bit strange and surprising. Deciding to investigate further, you take a fresh piece of paper and hold it closer to the rock. Again, small holes start to appear. What if instead of moving the paper, you move the rock? Now, nothing happens. Then, you move the paper next to the rock, and again, holes appear. Doing a series of experiments, moving and rotating around the rock and the paper, you continue to find that holes appear when you're holding the paper along a straight line directly away from one end of the rock. All right, what if you use two pieces of paper held along this line? Now you see holes appear in each, but you note that they don't appear at exactly the same time. The paper closer to the rock develops a hole before the paper farther away, and if we use more pieces of paper along this line, we see a succession of holes appearing as the pieces get farther away. So how do we explain these observations? Well, here's a simple hypothesis. Suppose that the rock, for reasons we don't yet understand, is periodically emitting small particles that travel in straight lines away from one end of it, and are capable of making holes in pieces of paper. This hypothesis is completely consistent with all the observations made so far regarding holes in paper held near the rock and the timing of when they appear. To summarize, we've taken a set of observations, holes in paper appearing in particular patterns, formulated a hypothesis as to their cause, invisible particles, and ascribed some properties to these particles, namely they penetrate paper, travel in straight lines, and move at a fixed speed. The speed we could actually determine by looking at the difference in time between holes appearing in papers held at a fixed spacing. To be clear, these are the properties that we've assigned to the particles in order to explain observed effects. But there's also the visualization we might draw of these particles. In this rendering, they're small purple spheres, but we don't actually know what color they are, or even that they have a color. They might be spherical. That could be an explanation for why the holes they make are round, but they might be cylindrical or some other shape. So we should be careful not to let our visualization mislead us into thinking the particles have properties they don't actually have. Now, the particle emission hypothesis is consistent with everything you've observed, until you try placing 2 or more pieces of paper on the opposite side of the rock. You again see holes appearing in sequence, but now the order is from left to right rather than right to left. Investigating further, you're convinced that these holes appear whenever papers are placed along a straight line emanating away from the right side of the rock. Since you now realize you get holes on both sides, what if you place one piece of paper on one side and one on the other, each about the same distance from the rock? Perhaps surprisingly, you observe that holes appear in each simultaneously. What could explain this? Well, let's modify our hypothesis slightly. Suppose instead of the rock mysteriously emitting single particles to the left, it's emitting particles in pairs, one to the left, one to the right. This would perfectly explain why you see holes on both sides and the timing of these holes appearing. So we again have a hypothesis that explains the observations. Now, we could be satisfied with the work done, but can we determine anything else about these particles? Well, you know that some objects are attracted or repelled by magnets, and some objects are unaffected by them. So you start playing around with magnets, trying to affect the path of these particles as they pass through pieces of paper. After some trial and error, you hit upon an arrangement that produces some interesting results. Between 2 sheets of paper, you place a set of magnets in a ring that the particles can pass through. Sometimes you see successive holes in the 2 pieces of paper as usual. The particle passes straight through. But other times, the holes in the second piece indicate the particle is deflected to the left, or deflected to the right. And if you like, you can put more pieces of paper along the path to see these 3 different trajectories more clearly. Now, you don't understand why you get different results for different particles, but to be able to easily do this experiment again and again, you take the whole setup of pieces of paper and magnets and put them inside a detector. The detector has an input on one side where a particle can enter. On the inside are the pieces of paper and the magnets, along with some electronics wired up to track which way each particle is deflected, and then tell you the result by turning on a light. The light going on means a particle has been detected, the same way a hole in a piece of paper detected one. Since the measurement with the magnets gave one of 3 outcomes, the light is configured so that it shows one of 3 colors, corresponding to each outcome. When a particle enters the input, the light shows either red, blue, or green. Now, we could have had an automatic readout showing the result was left, right, or center, or some other way of communicating the results. But in what follows, all we'll need to focus on is that we can do a measurement on these particles that gives one of 3 outcomes. And the colors are a nice visual way of viewing the 3 possible results. So we have a new observation about our particles based on the fact that this detector, with its magnets and pieces of paper, gives different results for different particles. How do we revise our understanding of these particles based on this observation? Well, the particles must come in 3 different types, or alternately, they have one of 3 different possible properties that cause them to deflect one way or the other in the detector and light up the different lights. Now, we could label each individual particle by what type it is, left, right, center, or 1, 2, 3. But since we're already keeping track of the type by the color of the detector light, it's nice to just color the particles to show which property they have. A red-colored particle causes the detector to light up red, a blue particle blue, a green particle green. Again, we can't see the particles all. As far as we can tell, they don't have a real color. The color of our visualization is just a convenient way of keeping track of the individual properties of each particle. With a detector setup constructed for easy readout and visualization, you can now take as much data on the particles coming from the rock as you like. Here's a sample for 20 consecutive particles. From all the data you take, there are 2 main observations. First, each type of particle appears with equal frequency, about 1/3 of the time. Second, the sequence of colored particles appears random. There doesn't appear to be any pattern, such as a blue one being more likely to come after a red one than a green one. Why do we see one type of particle rather than another? Right now, it's a mystery. But remember, we have no idea what's going on inside the rock that produces these particles to begin with, and maybe if we understood that process better, we'd be able to predict which particle was coming next. Now that was the data for the particles coming from one side of the rock, but you can use the same detector to check out the particles emitted in the opposite direction. Again, you find a varying sequence of red, green, and blue, And again, you can take lots of data that shows the sequence is random, with each color turning up a third of the time. Since the particles come in pairs, you spend a bit of time constructing a second detector so that you can measure both simultaneously. And here you find something interesting. Though the sequence is random, the colors you get on each side always match. Taking lots of data, we see that this is an ironclad rule. The measurements are always the same for each pair. With this observation, we can modify our hypothesis that the rock is emitting pairs of particles. It seems the particle pairs always come in the same color type, which then explains why the two detector lights always match. So, with more measurements and a revised hypothesis, we have a nice consistent story of what's going on. Thinking if there's any other experiments that could be done to test this hypothesis, you realize one day that the detector should work just as well if you flip it upside down. Now, in doing so, you've reversed all the magnets and sensors and electronics inside it, but you still have the input facing the rock, and trying it out, it works just fine. As expected, you get a random sequence of colors. You do the same thing on the other side and again see the random color sequence. And then you turn both upside down and see that they match. Not surprising given what we've learned so far. But then you ask the following. What would happen if one detector is right side up and the other is flipped upside down? And this is the Nobel Prize winning experiment. This is a Bell test. Now, Bell's original idea actually involved a measurement with two possible outcomes and three different detector orientations on each side. So what I'm presenting here with three outcomes and two orientations is again an alteration of the true story that spares us some mathematics. But the results will be philosophically interesting for similar reasons as the real experiments. However, before I get to what happens in our story, and to help build the suspense, it will be useful to take a few minutes to consider a possible outcome of the experiment that could have occurred in some alternate possible world. In this possible world, you find, somewhat surprisingly, that the colors on each side no longer match, or more accurately, that they don't always match. Sometimes they do, but more often they don't. Taking a slew of data on particle pairs, you observe that when the detectors are in opposite orientations, there's no longer any correlation between the colors on each side. A red one on the left is just as likely to be accompanied by a blue or green on the right as a matching red. Incidentally, you get the same lack of correlation if you invert the detector on the left and turn the other one upright. We can summarize the results in our possible world as follows. If both detectors are oriented the same way, both right side up or both upside down, then the colors match, and each color occurs with equal frequency. If the detectors are in opposite orientations, then we get all possible combinations of colors with equal frequency. What's going on? What hypothesis explains these results? Our earlier thought was that the particles are produced in matching color pairs, and the detectors measure which color particle goes into it. But the new results can't be explained with this hypothesis. What was wrong with our reasoning? Well, looking back on our story, we realized that we were potentially making a hidden assumption that isn't necessarily true. Namely, that a detector is measuring the same particle property whether it's right side up or upside down. Remember that in flipping our detector, we flipped all the magnets and everything else inside. So it wouldn't necessarily be the case that its output is going to be the same for the same input particle. From the new data, our old assumption is clearly wrong, and so we have to revise our hypothesis about the particles and their properties. Going back to the drawing board, we realized that it would have been more prudent to assign each particle at least two color properties rather than one. One property for each possible detector measurement one can make. So if an upright detector lights up blue, all we can properly say is that that particle must have had a property that causes an upright detector to light up blue when it enters it. We can designate, name, or label this property however we like, but a convenient visualization is to color the upper half of the particle blue to indicate that this particle will turn an upright detector blue when it's measured. Conversely, if this same particle would have caused an upside-down detector to turn red, it must also have had a property that causes upside-down detectors to light up red when it enters them. And we can indicate this property by coloring the lower half of the particle red. To account for all possible measurements of each orientation of detector, This means that rather than just 3 types of particles, there are 9 particle types, spanning all the different combinations of top and bottom colors. Sometimes these colors match, but they no longer have to. Though the particle coloring is now more complicated, what we should retain from our original hypothesis in order to explain the data is that the rock must emit matching particles. Let's see how this works for one possible pair of blue top, red bottom particles. If both detectors are upright, they both measure blue and thus match. If instead both detectors had been upside down, they would have both measured red and still matched, just as the data showed. However, if one detector is upright and the other upside down, then one will measure blue and the other red, so in our Bell test they don't have to match. If each pair of our 9 possible colorings is equally likely, this perfectly explains the results of the experiments with matching detector orientations and the initially surprising result of our Bell test. So we have a revised hypothesis that is again consistent with the measurement results. This all works out nicely, except for the fact that these were the results in an imagined possible world. But these are not the results you get if you do this Bell test in our world. In our world, you get these results. At first, these results might look similar to the possible world. Each detector still measures each color randomly with equal likelihood, and the colors in each pair don't have to match. But notice that now you never see matching colors. In fact, if you stare at the data a bit more, there's a correlation between colors. Whenever the left detector is red, the right one is blue. When the left detector is green, the right one is red. And when the left one is blue, the right one is always green. Note you can also run the experiment with the left detector inverted and the other one right side up, and you see the same correlation. Let's summarize the results in these tables. If the detectors are oriented the same way, we always get matching colors, though which color we get appears random. If the detectors are oriented opposite each other, we get either red-blue, blue-green, or green-red. Again, with each of these results occurring randomly with equal chance. Now, how can we explain these results? What properties must the particles have? Let's think carefully about one possible experimental result. Suppose the detectors were opposite, and we observed red on the left and blue on the right. We assume that the particle on the left must have had some property that causes an upright detector to light up red, and the particle on the right must have had some property that causes an inverted detector to light up blue. Again, we could designate or label these properties in many ways, but let's use our visualization trick of coloring the upper half of the left particle red and the lower half of the right particle blue. The upper half color is a way of specifying whatever property a particle has that turns an upright detector that color, and the lower half color of specifying whatever property it has that turns an upside down detector that color. Now, though you performed measurements on these particles with the detectors in opposite orientations, what would have happened if you'd measured the same pair with the right detector upright instead? Well, since the left detector showed red, and the 2 detectors always match when they're in the same orientation, the right detector would also have shown red. Thus we can conclude that the particle on the right must have had the property of turning upright detectors red, and we can color its top half red to specify this property. Now what if instead you'd measured this pair of particles with both detectors upside down? Well, you did measure the right particle with an upside down detector and got blue, and since detectors always match when they're the same orientation, that means you would have gotten blue on the left as well. Thus, the particle on the left has the property that it can turn an inverted detector blue, which we can designate by coloring its lower half blue. So from the established experimental correlations above, we figured out the properties this pair of particles must have had. There's just one problem. Suppose instead of measuring the pair with the left detector upright and the right one upside down, you had the left one upside down and the right one upright. Based on the properties we've assigned the particles, we would then predict blue on the left and red on the right. But from our data summarized in the table above, we never see this result. The particle pair can't have been a matched pair that caused upright detectors to turn red and inverted detectors to turn blue. What went wrong with our deduction that led us to this mistaken conclusion? I would encourage you to think carefully about the steps in our reasoning. would there have been some other way of coloring or labeling the particle properties, maybe using a more complicated combination of colors, or colors that change in time, that would have avoided making a bad prediction? If you try it out, you'll find that by specifying each particle has a set of properties that predict the detector results, you'll always make this bad prediction. So what can we do? What assumption did we make that led us to this incorrect prediction? Well, a central assumption of our argument was that before they were measured, each particle must have had properties that determined the outcome of a measurement on it. If this was the assumption that led us astray, then we have to throw it out. Just the assumption that the particles had properties that caused the measurement outcomes will otherwise lead to incorrect predictions. This conclusion means that we can't color in the particles or assign them properties with labels or numbers or names in a way that determines these measurement outcomes before a detector measurement is made on them. Can we say anything at all about their color properties? Well, yes, we can say everything we know about the possible outcomes and correlations that is summarized in our table. And this collection of information is known as the quantum state of these particles. The quantum state of an object or group of objects is a description of the possible results for all possible measurements and all possible combination of measurements. And quantum mechanics is mainly a technique for constructing such tables, or states, for different physical situations and physical systems. Though the table contains many possible outcomes of many experiments, it's the whole table that constitutes a single quantum state, describing one pair of particles. Notice that even though our table has lots of information, it doesn't tell us everything we might like to know or predict. In particular, all those or possibilities means that the quantum state doesn't tell us the outcome of any single measurement on one of these particles. It only informs us we'll get red or blue or green with equal likelihood. This may seem like a failure of quantum mechanics and a shortcoming of the quantum state description. Shouldn't a good physical theory tell us exactly what's going to happen when we measure a particle? Maybe there's a better theory that tells us this information. But the hope of being able to color in some additional information about the properties of particles that predicts the measurement outcome, often called hidden variables, is precisely what the Bell test has apparently ruled out. Assigning these types of properties to the particles will lead to bad predictions. Thus, all we can safely say about the particle's properties and measurement outcomes is what the quantum state table tells us. Another way of putting the state of affairs is that the Bell test results undermine our expectation of what's termed local realism. An object in a particular location, that's the local part, should have real properties, that's the realism part, that determine measured outcomes. The Bell test results imply you have to give up your expectations about things being local or really having certain properties, or both. Another common word used in quantum parlance is uncertainty, which is supposed to indicate the state of affairs that the particle doesn't have certain properties. However, this word is often seen as a bit misleading, since uncertain implies that the particle has properties, but we don't know what they are, which is not the conclusion we've come to. Regardless of our knowledge, the particle can't have certain properties at all. A better word might be indeterminacy. Nothing we could know or learn, including understanding what's going on in the rock that produces these particles, could ever determine their color properties before they're measured. They simply don't have color properties. The other word that gets used frequently when discussing Bell tests is entanglement. The two particles are said to be quantum mechanically entangled, since the outcomes of measurements on both of them are correlated, such as is shown in the table above. Now, in popular accounts, entanglement is often presented as an obscure or novel phenomenon, but in fact, it's an incredibly ubiquitous phenomenon. Almost any time things are interacting with each other, there's some form of entanglement going on. To cite one example, you've probably heard that things like rocks are made of atoms, like carbon and hydrogen, and that these atoms are held together by chemical bonds, often drawn as a line between the two atoms. What does this line mean? Well, it signifies a pair of electrons shared between the two atoms, a pair of entangled electrons. Just as in the Bell experiment, there are properties about each of these electrons that are indeterminate, even while the correlations between them are determined. So entanglement isn't just a physics lab phenomenon, it's what's holding you and everything around you together. What makes the particle entanglement in the Bell experiment interesting is that though the entangled particles started out close together in the rock, they could be separated by large distances, literally miles apart, to form a non-local pair of entangled particles. This separation enables a particularly noteworthy variation of the experiment to be conducted. Instead of having each detector at the same distance away from the rock, what if you move the detector on the right farther away? Now the detector on the left measures its particle first. Let's say it registers blue. Immediately, three things happen. First, the measurement changes our quantum state, and this is a general feature of quantum mechanics that measurements change states. From our table of possibilities, we can discard the or possibilities that aren't consistent with a blue particle on the left, and get a new quantum state, a revised table of possible measurement outcomes. This revised table coincides with the second change the measurement on the left particle produces. We can now exactly predict the outcomes of either detector measurement for the particle on the right. If you measure it with an inverted detector matching the inverted one on the left, you'll get blue, while an upright detector will register green. This means that we can now, and only now, assign properties to this particle that are consistent with these definite outcomes. You could even choose at this point which measurements to make, flipping your detector one way or the other, and you'll get a result exactly consistent with the predictions made by the particle's newly assigned properties. The third thing that happens when the one on the left is measured is that the entanglement disappears. The entangled correlation between these particles meant the measurement on the left determined the properties of the particle on the right, but once this is determined, there's no further correlation between them. The fact that a measurement on the left spontaneously determines the properties of the particle on the right is known as the Einstein-Podolsky-Rosen paradox, or EPR paradox. After a 1935 paper, these authors wrote, pointing out the surprising prediction of quantum mechanics. Einstein termed the measurement of one particle creating or changing properties of the other particle a spooky action at a distance, and was particularly concerned that it implied some faster than the speed of light communication between the particles. It turns out that you can't actually use this effect to send information instantaneously from one place to another, though scientists are actively researching schemes for using it in other ways. Both Einstein, in pointing out the counterintuitive nature of the quantum predictions, and Bell, in proposing a specific test to check these predictions, held out hopes that the quantum predictions would turn out to be incorrect, and reality would turn out to be more intelligible and intuitive. However, the series of experiments that merited the Nobel Prize, ever more precise variations of the Bell test we've discussed in this video, confirmed the counterintuitive predictions of the quantum reality we live in. Perhaps less technically, they showed that certain sets of otherwise reasonable assumptions about how reality works turn out to be inconsistent with observations. As I hope you now have a better sense of what these observations are, you can go back through the chain of reasoning and think about what assumptions you have about reality and which ones you might want to change or throw out. For example, remember that we never actually see these particles we've been measuring. What should you assume and not assume about their existence? For that matter, what determines whether something exists anyway? You might start by asking this question about something whose existence seems obvious, like, say, a rock. How do you know the rock exists?